Okay, today is our last major topic of integration. Partial fractions, or what we call partial fraction decomposition. But there's a lot of groundwork that we need to lay before we actually get into these problems. I guess in my experience with this, if I don't lay this groundwork, then it might be even more challenging. So let's start by looking at some preliminary concepts. I'm going to say for 6.3, partial fractions. We're going to start with what I'll call prelim concepts. Some things we should just be aware of before we get into this. Let's take a look at some integrals that are going to come up throughout this section so that we're ready for them, we're quick with them, we don't have to spend a lot of time on them, all right? So something like this. Let's integrate 1 over x plus 1 dx. What I want you to see on this example is that this is a quick substitution. U would be x plus 1. What's du? dx. This integral becomes integral 1 over u du. Correct? Antiderivative of 1 over u is natural log u. Absolute value of u, right? Plus a constant, but what was u in the problem? X plus 1, right? So what we should be able to do today is if we see something like this, not have to go through all these steps and just be able to say, oh, that's just natural log of x plus 1, right? Here's another one similar to that. What if we have 1 over x plus 1, this time squared dx? Could I make the same exact substitution? Yes. Make u be x plus 1. Then what would this integral turn into? Integral 1 over u squared. Could I write that as u to the negative 2 just to make our integration a little easier? The antiderivative of u to the negative 2. Negative u to the negative 1, right? Negative u to the negative 1. Agreed? Or I could write it as negative 1 over u. That okay? So this is just power rule, right? The antiderivative of u to the n is 1 over n plus 1, u to the n plus 1. I'm doing that kind of mentally. This is plus c, so negative 1 over x plus 1 plus c. Same thing that we did here. Yep. Nope, just x plus 1. And of course, I could do this again, like integral 1 over x plus 1 to the third power, right? The only difference now would be, our new integral would be u to the negative 3, right? Instead. So same substitution, u is x plus 1. And we would get, antiderivative of this would be negative 2, it would reciprocate, right, and come up. Maybe I need to show this. This would become 1 over u plus 1. Oh, wait, no, you're right. 1 half u to the negative 3 plus 1. Yes? Y'all agree with that? That's the actual power rule. So it would be negative 1 half u to the negative 2 plus a constant. And then that would be, if I rewrite it, negative 1 over 2 x plus 1 squared plus c. The whole point here is that when I get to this today, we aren't going to show all this, all right? We're just going to get right to the answer. But I just want to make sure everyone's aware of what we're doing when I get to it, okay? Any questions? What would change if I did an integral that looked like this instead? So instead of giving you x plus 1, I give you ax plus b. So I give you a linear expression. What did we have to do whenever we were integrating and we had that linear thing inside? We always had to come through and do 1 over a, didn't we? 1 over a to compensate for that. So, but this right here is just like this first one here, isn't it? Just turns out to be a natural log. But I need what in front? The constant, right? So this should turn out to be 1 over a natural log ax plus b. I'm not showing any of that work. And then if we took that linear expression in the denominator ax plus b and this time squared it, we would still need that 1 over a out there, wouldn't we, to compensate for the a out here? So it would be, what? 1 over a times negative 1 over ax plus b. I'm getting that from this one right here, right? This right here. All we're doing is the same answer, except replacing x plus 1 with ax plus b, and then compensating for the constant by coming through the 1 over a. If you're not happy with this, on these problems, just do it by hand slowly on your own. Make the substitution u is ax plus b. Just make that substitution and work through the whole thing, and you'll get to these results. Okay, going to move on. Next concept. Still just getting things in order here in our heads. What if you had an integral that looked like this? Integral 2x minus 3 over x squared minus 3x minus 4 dx. Even though this integral does look a little complicated, right? I want you to notice something. The denominator is a quadratic, isn't it? And the numerator is linear. When you take the derivative of a quadratic, don't you always get something linear? Like if you take derivative of something x squared, blah, 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 the derivative, the power comes down by 1, so you always get something linear. And notice that exactly the derivative of the bottom right here, what is the derivative of the bottom? It's this exactly up here, isn't it? So if I let the bottom be u, right, if I let u be the x squared minus 3x minus 4, then I have exactly 2x minus 3 dx. That's the derivative. And that's exactly what appears up top. And I'm really, really happy to see that, right? Because I can replace 2x minus 3 dx with du, and then the bottom here becomes a u. So this integral really just turns into 1 over u du, doesn't it? And that's natural log u plus c. Do you see that? And then I replace my u with whatever u was, which is that entire quadratic. So if we ever have an integral where we have a quadratic expression in the denominator, it sure would be nice to have its exact derivative up top, wouldn't it? I mean, because then it would always just turn into this. Yes?
How did you know to change the 2x minus 3 in the numerator to 1?
I didn't. I replaced 2x minus 3 dx with du. And I slid the du out here and just left a 1 on top. So I just made my substitution and this substitution into this and came up with this. Now, how would things change if I did something like this? Integral 2x minus 3, again, over x squared minus 3x minus 4 squared dx. Would that change a lot of things? No, because it's the same substitution, isn't it? U is equal to the bottom, the du is up here. The only difference is when I rewrite the integral, I would rewrite it and it would be what? 1 over u squared, and 1 over u squared we can find the antiderivative of. Yes? Okay. So making the same substitution as I did above, I would get integral 1 over u squared du. The antiderivative of that is negative 1 over u plus a constant. That's what we did just a minute ago, right? So we would have negative 1 over x squared minus 3x minus 4 plus a constant. Are y'all following how this is kind of building a little bit? Now, I could keep going with this idea where I could put a cubic function in the bottom, right? A cubic expression. And then what would we need in order to do the same sort of thing? We would need a quadratic, and we would need it to match exactly, right? But if they do match, we're in business, all right? If they match, we can just go straight to this. You know what I mean by match? The derivative of this is that? Okay. Now, if what's up here is not the derivative of this, we will have to grind it out, but our goal will be to get it like this. All right, what about this? Integral 1 over 1 plus x squared dx. You should recognize that, right? Antiderivative of that? Arctangent? Arctangent x plus constant. That's just a known formula. That's one of those ones we just have to have kind of hardwired now. Now, what would happen if I change it up a little bit and I put in here something like x minus 3 squared dx? I could just replace this x with this, right? X minus 3. And so the answer to this would be arctan x minus 3 plus c. But what about this one? What's that? You got to account for the 2. So you'd have to put a 1/2 out front. Okay? You'd have to put a 1/2. So the same thing that we had before, it's compensating. If that's a linear, if this is a linear expression, that's what you're really doing like a little mental U substitution on. You're going to have to kill off that a in front by coming out with a 1/2, a 1 over 2. Then arctangent of 2x minus 1. All right. Let's take a look at something that's kind of interesting. I didn't plan on doing this, but I think it'll be fun. Who said that? I didn't say fun, did I? What if we have 2x plus 1 over x squared minus 3x plus 4 dx? Sorry, I have to think through that one a little bit. So do we have that form where the bottom's quadratic and the top is linear? yeah, okay, it is quadratic and linear up top. So I would hope, I'd really be happy if the derivative of the bottom was the top. Is it? No, it's not. However, there is a workaround, all right? And here's the workaround. I'm going to make my denominator x squared minus 3x plus 4. I'm going to make that u. The derivative of that is what? 2x minus 3 dx. And I said, man, it sure would be nice if I had 2x minus 3 up top, right? Wouldn't that be nice? So I'm going to make it happen. I'm going to say 2x minus 3, right? But I can't just subtract 3 unless I add 3, and then what was still up there? Plus 1. Now you're sitting there going, what the hell are you doing? You're making this more complicated. Why are you doing all that, right? Do you agree, first of all, that that's true? Yes? Now I can put these two together, right, just side by side, and then I can put these two together. That becomes a 4. So I could really write this as integral 2x minus 3 plus 4, yes? And since I have two things on top and one big expression on the bottom, I could split it into two separate integrals, couldn't I? And the two separate integrals would look like this. The first one would be 2x minus 3 over that whole denominator. And then the other one would be plus, because I have a separate integral, 4 on top over x squared minus 3x plus 4 dx. You follow? Now the first one is, I don't want to say easy, but it's very doable because I have the derivative is exactly up there, right? So that just turns into basic substitution. U is the bottom, there's du, so we're doing integral 1 over u, so natural log, right? Okay, so this one's just going to become the natural log of the entire denominator. That's my answer, no more integral, right? I just took the antiderivative, plus c, but I'll get to that later. This one, however, is quadratic on the bottom and linear on top. I mean, not linear. It's linear because 4 is a line, but it doesn't have x, right? Doesn't have x. So how do I deal with that? Pull the 4 out? Is that what you're saying? I can pull the 4 out, yeah, and then I'd have 1 up there, right? But look back up the previous problem that we did. Look right here. Look at this right here. I want you to just focus your attention on this. Had I decided to just, could you FOIL that out on the side over here? 2x minus 1, 2x minus 1, FOIL it out, and then combine it with this 1. And wouldn't you have a quadratic on the bottom and a number on top? So what do you think the process is going to be for us here to make it look like the one I just showed you? Completing the square. We're going to complete the square on this. If we complete the square on this, then we will be able to do exactly what I showed you a second ago. All right? So let me complete the square on this right here. I'm going to complete the square. So the way we complete the square, we take the quadratic. We put it in order, descending order. We make sure that the leading coefficient is 1. If it is not a 1, we have to factor it out and deal with it. But fortunately for us, it's a 1. If it's a 1, then we look at the number in front of x. The number in front of x is negative 3. So I take negative 3, and I divide it by 2. I always will do that. You always do that for completing the square, right? Then you do what? Square it, which gives you 9 over 4. And so what I'll do now is I'll rewrite the exact problem I had, except right after the 3x, I'm going to add the 9 over 4, and then subtract the 9 over 4. And then what did I still have there? Plus 4. Agree? Okay. Now, when you do this, you're guaranteed that the first 3 terms are going to factor. is a perfect square trinomial, which just means it's parentheses something squared. So it'll be exactly x and then something squared. But what will always be the number that goes here? This thing that you squared up here, the negative 3/2. So you're going to put negative 3/2 right there. And then you have everything else that you haven't messed with here, which is negative 9/4 plus 4. So what's negative 9/4 plus 4? Negative 9/4 plus 4. 16. We're adding though, right? So 7/4. Everyone agree? 7. Yeah, it's negative. So 7/4. So 7/4, and that's it. Well, isn't that nice? So I'm coming back up to this integral. I'm pulling the 4 out. I'm pulling this 4 right here out. And then I'm rewriting the denominator to be this. 1 over x minus 3/2 squared plus 7/4 dx. Follow? Now I want to point you to a formula. Okay, there's a formula on your formula sheet. It's the one for arctan, but there's something in the formula that is subtle we need to point out. Number 17 formula says the integral, 17, yeah, 17. It says du over a squared plus u squared equals 1 over a arctan of u over a plus c. Y'all see that? Every problem we've pretty much done up to this point, the a here has been what? Has been a 1, right? It's been a 1. But in this particular problem, it is not a 1. So we need to figure out what the heck that a is and then make sure we apply it to our formula. Notice that if it is a 1, this is just arctan of u, and that's it. We're done. So since I'm going to go back and put an answer, let me write down the integral that's on the other page. It was the 4 came out. I'm just going to put it there. And then it was x minus 3/2 squared plus 7 over 4. Now, we do not, when we do this, we know it's going to be an arctan. We just have to make sure we get all the constants correct here. There is no number in front of x, right? Well, there is. There's a 1, right? So I do not have to worry about coming through and dividing through by whatever's in front of this, so because it's a 1. But this right here is a squared, right? This right here is a squared. So that means a is what? Root 7 over 2. Root 7 over 2. You take square root of top and bottom. And therefore, I forgot my dx on this. Sorry. My dx right there. I forgot it when I wrote it. Therefore, the antiderivative of this will be 4. Okay. Now let me start plugging into this formula. 1 over a. What's 1 over a for us? The reciprocal of, so 2 over root 7. Arctangent of whatever's in the parentheses, right? Our u is this. That's our u, right? X minus 3/2 divided by that root 7 over 2. So it's the x minus 3/2 over the root 7 over 2. And then plus c. You can clean this up. You could flip the 2 up to the top. You could even distribute the 2 through. But that's as far as I'll go. I want to do a quick little, well, I need to finish putting the final answer together, don't I? Okay, so I'll distribute that 4 through, and I'll do that on my answer here. So back to this. It was natural log x squared minus 3x plus 4, and we just did all that work to figure out that it was plus, was it 8 over root 7? Arctan of 2 times x minus 3 halves over root 7 plus a constant. Y'all feeling okay? We still haven't started today's stuff, but is this at least, I mean, this is new, I guess, but are there any questions on it or any negative feelings? I wanted to ask you a question, and this is off topic, and I don't want to waste too much time on it. But how many of you have been told never to leave a radical in the denominator when you write an answer? Have you been told that before? Has anyone ever given you any explanation as to why? Do we care? So I was told the same thing. It always bothered me why I couldn't just leave this answer 1 over root 2, and they always wanted me to convert it to this, right? Multiply top and bottom by root 2. And there's no real, I guess, no one's going to be able to tell you what the advantage is to doing this, other than it's a good exercise in multiplying by 1. You know, you get to practice multiplying radicals, big deal. But as someone who should be able to do that anyway, at this level, do we really need to rationalize denominators? The answer is no, we don't. But why are you told to do it? So let me explain to you why. This is what I think it is. Because before calculators, before computers, you ran into numbers like pi, e. I mean, those numbers were still there back before computers and calculators. Square root of 2. These are things that we'd see a lot of. I say we, people before computers. They would see those a lot. So they would need to know what their numerical values were. And they would have to have them memorized. So everyone would have to know, pi is approximately 3.14, 15 or something like that. And they would have them memorized out within a certain tolerance. And it was almost like showing off if you could say like pi out, 20 digits or 30 digits. That made you cool, You walk around, you had your slide rule, you didn't have your calculator. And in fact, I teach with someone a fellow faculty member, I won't mention who they are, but they know pi out, I think 60 digits. They at one time knew it out 120 digits, and I believe the record is 60,000 or 16,000. I forget. That's the record for a human memorizing it. Okay, I'm getting way off topic. And then e is approximately 2.71 something, right? And then square root of 2 is approximately 1.414, right? So they would have to know those, right? But then they would run into a problem where they would need to compute what this is. Now that wasn't as well known. Or maybe it was like 3 over that or something. So they would rationalize it. Now here's why it was good for them to do this. I'd like for us to take this right here, and we'll leave it as a 1 just for demonstration purposes. I'd like for you to try and divide without a calculator 1 divided by the square root of 2. So you go back old school style, right? Old school division bar. You put a 1 there, and on the outside you put what you've memorized, because you don't have a calculator, but everybody knew the square root of 2 was 1.414, right? So you put that out here, and then you start dividing. And so you ask yourself, well, how many times does 1 go into 1? It doesn't, so I have to put a decimal here and then a 0. So then I say, well, how many times does 1.414 go into 10? I don't know. Yeah, no, you're not allowed to use a calculator. Okay, so screw that. Let's go to this. Okay, if we do that, what's the square root of 2? It's 1.414, and then what am I dividing it by? 2. How many times does 2 go into 1? It doesn't, so I bring up a decimal. How many times does 2 go into 14? 7. Bring it down, subtract, right? I get a 1, a 4. It doesn't go into 1, but it goes into 14, so 0 and then 7. So much easier to do by hand, right? You follow that? Now, go ahead and do square root of 2 divided by 2 on your calculator. You're going to get 0.707 something. And it was so much faster this way. So it was out of necessity that the rationalization occurred because it made it easier to do by hand. But with calculators, we don't need it, right? And the answers are exactly the same. You do that on your calculator, you do that, you get the exact same answers, so who cares anymore to rationalize it? That's just my opinion. You'll run into another instructor who's going to tell you, rationalize your denominators. And I would just listen to them if that's what they want, but then I would ask them, why? Why? Why do I need to? Same answer, right? All right. Sorry, let's go back to this. All right. Are we ready to get into what today's? Oh wait, there's still one more preliminary thing. Damn it! Thought I was done. Just make sure we all remember long division. Long division. Long division's taught different ways. I've seen all sorts of unique methods, but I'm going to show the one that's taught most often in books, at least books in the United States. I've seen some really different methods used throughout the world, but what if you had a rational expression like this, where the power in the numerator was bigger than the power in the denominator here, which is 1. If that power on top is bigger than the one on bottom, or if they're the same, you can always use long division to rewrite this expression. So the way we do it, we take the numerator, which in this case is x cubed plus 7, and we rewrite it as x cubed plus 0x squared plus x plus nothing. So I'm just rewriting the third degree polynomial, just kind of ripping it apart, making sure I account for any spaces or missing terms with 0 terms. If you forget to do that, then things don't line up later and it gets a little confusing. So we do that, and then on the outside we put what? The x minus 1. And then what is it that you ask yourself? How many times does x go into x cubed, right? Which is, well, not how many times you're saying, I guess you could say that. What do I multiply x by to get x cubed, right? X squared. And then what you do is you distribute that to each one. So when you distribute that here, you get x cubed. And then when you distribute the x squared to -1, you get negative x squared. So I'm lining it up underneath. And then we come through and we subtract this row, don't we? We subtract it. So we change its signs. So this becomes a minus x cubed, and that becomes a plus x squared. I like to really exaggerate that we change the signs. And then you add down. When you add down, what do you get? X squared plus x, and then you don't have to bring the 0 down. And then you ask yourself the same question. How many times does x go into x squared? Well, x, so I need to, I don't like that. How many times? What do I multiply x by to get x squared? X. So then you multiply x times x minus 1, and you get x squared minus x. Change the signs. Add down, you get 2x. When do I stop? When the power of this is less than the power of this. And right now they're the same, so I can keep going. What do I multiply x by to get 2x? A 2. So I put 2 there, distribute again the 2 over, so I get 2x, what? Minus 2, come through, change the signs. Add down, I get 2. So now I stop, right? This is my remainder. So what we do is we come back up here and we put plus the remainder over the divisor. There. This expression is equivalent to this expression. Agreed? Now, why would I want to do that? Yeah, what if I asked you now to integrate this? It's not a basic substitution. It's not integration by parts. It's not a trig integral. It's not a trig substitution. It's not one of the ones we just did where it's quadratic down here and linear up here. However, by recognizing that the power of the top, it's polynomial divided by a polynomial, so recognizing the power of the top is bigger than the bottom, I can do the long division. When I do long division, I can rewrite the integral to be all those terms, right? Which we're up here, x squared plus x plus 2 plus 2 over x minus 1. And now I can do term by term integration. The antiderivative of x squared, 1/3 x cubed. Antiderivative of x, 1/2 x squared. Antiderivative of 2, 2x. Antiderivative of this, yep, what would that be? That's right. Remember this, right? Right? We said if we have that, something like that, it's just natural log. So 2 natural log x minus 1. That's what we get there. So our answer here would be 1/3 x cubed plus 1/2 x squared plus 2x plus 2 natural log x minus 1 plus a constant. See that? So this would have been very difficult to just go after without this long division. So long division is just another tool we have in our toolbox now. We will apply long division anytime we're kind of stuck and the numerator's degree is greater than or equal to denominator. All right. So I'm going to get into partial fractions now, but I want us to start by looking at something, and then we'll discuss partial fractions in just a second. I mean, this is part of partial fractions, but I just want you to think about this right here. If I told you to combine these so that they have the same denominator, in other words, subtract these fractions, you would have to get common denominators, right? And then put them together, which means you would have to introduce an x minus 2 on this one, and then on this one you'd have to introduce what? X plus 1, and then you put them together and they have the same denominator, right? And when you do that, you would get the x minus 2, you'd have the minus 4 times x plus 1, then all over that common denominator, which would be, I'll do that next step, but yes, it would be just those two denominators together, right? And then I could clean it up, distribute through on top. See, how many x's will I have on top? -3. -3 x's. And then distribute this, -4. So -6 up top. Over, now I'll distribute through the bottom, x squared minus x minus 2. So this is the same expression as this, right? My question to you, which would you rather integrate? Would you rather integrate this, or would you rather integrate what's up there? What's up there, right? Because how would you integrate each one of these? Those are just natural logs, aren't they? I mean, that's what we started with. The antiderivative of this would just be natural log of x plus 1 minus 4 times the natural log x minus 2. We're done. We move on, right? If we had this, we have x squared minus x, so we say quadratic, linear. We're starting to get excited. Then we realize that the derivative of this is not up there. And we just saw how much work we had to do to make that happen, right? And actually, this is even harder than the one before because it's a 3 out here, not a 2. And I'll show you how to do one of those later, and you'll appreciate the difficulty in it. But for now, we would not like to have this, right? This would, well, along with some other stuff to get this one to work out. So if we're faced with something like this, wouldn't it be nice to turn it back into this? Well, the process of going from this to this is called partial fraction decomposition. It's something that hopefully you were shown in pre-cal or somewhere else. You go from here to here. And so that's what we're going to do today. Today's section, partial fractions, has to do with how do we handle these polynomials, rational integrands, where we're just trying to get them to be easier. And part of the technique is this partial fractions. All right? So how do we do it? Start with this example, the same one that we just did. Let's act like we don't know where it came from. We know where it needs to go, right? We know what the answer needs to be. Let's see if we can get there without knowing that. So the first thing you do when you're going to apply partial fractions is make sure, like if this isn't an integral, which I'm not putting in the integral yet, but if this were an integral, the first thing you do is make sure that it's not just a quick substitution, right? But let's just focus on the partial fraction part of this, the breaking it up. I will first make sure that the denominator's power is bigger than the numerator. Because if it's the other way around, what can I do? Long division. Okay, so I am looking, power here is 2, power there is 1. I cannot do long division. Therefore, the only thing left to do is try and do partial fractions. So I will factor the denominator. That kind of makes sense to factor that. Because the power on top is smaller than the power on the bottom. So if you were to try and do that division box, you'd be trying to turn x squared into negative 3x, and you can't. You could, but you can't. That's just even more complicated because you have to multiply by like a reciprocal, like 1 over x or something. Okay, so that makes sense? Now, the idea of partial fractions is that we know, we need to know that this does break up to be 2 things. The reason we know that it breaks up to be 2 things is because there are 2 factors. And we know that underneath the first fraction, we have the first factor, and underneath the other one, we have the other factor, right? What we don't know is the numbers on top, right? We don't know what those are. So we're going to represent them with letters, capital A and capital B. Our goal is to try and figure out what A and B are. All right? So let's listen to some of the language that I'm going to use right now because it's going to come up later. Right now, I have 2 distinct linear factors, right? I have 1, 2. They're both linear. They're being multiplied, so they're factors. They're distinct because they're not the same. If I had x plus 1, then I would have 1 repeated factor, linear factor, repeated. These are 2 distinct linear factors. For each distinct linear factor, I placed it in the denominator, and on top of it, I placed a constant. For this distinct linear factor, I put it in the denominator over here and placed a constant on top of it. And that's kind of the idea behind partial fractions. When I give you that handout the other day, it had partial fractions on it. I'll go and we can look at that in a minute and show what I'm saying right now and how it's written and kind of make the connection, but I don't want us to get our faces in the formula sheet yet, all right? Because it'll look overwhelming. Okay, here we go. I'm going to try and go and figure out what A and B are, right? That's my question. What's A? What's B? If I can figure out what A and B are, I'm done. So I'm working with this. I'm assuming that this equation right here is true. If this equation is true, then you can multiply both sides of the equation by the LCD. So I can multiply both sides by this, right? That's the LCD. If I multiply the left side by this, it goes away completely, and I'm left with what? Negative 3x minus 6. And if I multiply the right side by the LCD, when I put the LCD right here and multiply x plus 1, x minus 2, what happens? X plus 1's cancel, and you're left with a times x minus 2, and then what's the other one going to be? B times x plus 1. Show of hands, how many of you saw this partial fraction stuff? All right, good part of you have seen it. And now what? There's kind of like two approaches at this point. One approach, the easiest approach, but it doesn't always work, is to just start picking some values of x and seeing if you can figure out what a and b are. So, for example, if I want to know what a is, wouldn't it be nice if b wasn't even here? Well, how can I kill b? If I'm allowed to control x, if I let x be negative 1, I can kill off that b factor, right? So watch. I'm going to say let, this one of the few times in math that you're actually allowed to do something you want to do. You can let x be something, all right? So I'm going to let x be negative 1. If x is negative 1, I'd like for you to rewrite this entire line. What would you get? Replace all your x's with negative 1s. 3 minus 6, so negative 3 equals a times negative 1 minus 2 is negative 3, and then plus b times what? 0, and that was the whole idea, is it killed off this. And so this is really negative 3 equals negative 3a. And divide both sides by negative 3, and you get a is 1, right? So I know what a is now. I'm happy. How am I going to get b? Let's kill off the a, right? So now just come in here, little God complex again. Let x be 2. Let it be. And it is, and it was good. Right? Okay, so here we go. X is now going to be 2. What do I get if I plug 2 in right here? Negative 6, negative 12, and then a, I know that's going to be a 0 in there, plus b times negative 2 plus 1. No, not negative 2. 2. So 3. That's gone. So negative 12 equals 3b. So b is negative 4. And that's it. That's what I wanted, right? What's a? What's b? Now come back up here. Make sure you put the a in the appropriate place. We said a was what? 1. So 1 over x plus 1, and then b was negative 4. Does that match what I had done to start this over here? Yes. It was 1 on top of the x plus 1, and then the negative 4, notice that the negative is the minus out here. So it's positive 4, but change that to minus. That's the easiest approach for these. But like I said, it doesn't always work. I would always try it first, because if you can nail down a and b right away, you're in business. What's the other approach? So I would like to show you the other approach, because I've got to make sure you know how to do it. I'm going to take this and go to another page with it and rework it with the other approach, because you're expected to be able to do either one. Okay, the other approach, which is more powerful, this will work no matter what, all right, is you distribute your constants through. So what we're really doing is we're just expanding everything out on the right side. ax minus 2a plus bx plus b. So expand the right side. Then collect like terms. Collect like terms on the right side only. So do you agree that ax and bx are like terms? They both have an x in them? So I'm just going to write them side by side. They're now friends. ax plus bx. And then negative 2a plus b are like terms. Why are those like terms? They're really both numbers, aren't they? These are both just numbers. A is a number, B is a number. You put them together, it's a number. So these are like terms. If I knew what they were, I'd put them together. And here, these both have the x, so I can put them side by side. The left side of this is still negative 3x minus 6. Now, I'm going to do something kind of interesting here. I'm going to factor an x out of the first two, but I'm going to factor it out on the right side. It's the same thing, right? And then back here, I'm going to put plus, and then I'm going to put the other two like terms, the negative 2a plus b, back here in parentheses. And on the left side, negative 3x minus 6. Now, what I'd like you to see is that the number sitting in front of x, right, negative 3, if this equation is supposed to be true, then the number sitting in front of x here needs to be equal to the thing in front of x here, doesn't it? And the number that's by itself, minus 6, must be equal to this number back here. We said that's going to be a number at the end. Those have to match. Negative 3 has to be what I get when I put a plus b, and negative 6 has to match up with what I get when I do that. Do you all follow that? The x is just our variable, and it's going to be there. So what I can now do is write down those two conditions. And when I write them down with a big brace in front of them, and put a plus b must be what? Negative 3, and negative 2a plus b must be negative 6, I now have a system of linear equations. And if you have a system of linear equations, you can usually solve that system of linear equations as long as you have as many equations as you have variables. So I have two variables, I have two equations, I should be able to get a unique solution. And now you use either elimination or substitution to solve this, right? How many of you feel like you could solve that by hand? How many of you would know how to solve that on your calculator? Yeah. What if I gave you a system of 3 equations and 3 unknowns? Feel like you could do that by hand? What if I gave you 5 equations and 5 unknowns? It's going to take a while. Okay? I am a big fan of us not being dependent on the calculator, but this is the one time I think everyone in here should know how to program, to know how to solve a system of linear equations on their calculator. Because I can guarantee almost everybody in here's calculator can do it. Even if you got like the TI-83, you know, the basic one. They all have the correct function in them to be able to solve this. So when we get to a problem that's more involved than this one, I'll probably show you how to do it. How many of you have your calculators here with you? Okay. If you don't, you'll just want to take note and get back with me later and make sure you know how to do it, all right? But let's just get to another example before I show you, all right? I'm just going to trust that everyone here could solve this on their own and get the two solutions, 1 and negative 4. Which way do you prefer here? This way or this way? This way was real quick, right? But like I said, it doesn't work every time. We're going to see an example of that where it won't work. So we have to have a fallback method, and this one is our fallback method. We are ready to start doing partial fraction integrals. All right. All right, so when we do a partial fraction integral, if you are one of those people that kind of like steps, I can give you a few steps, all right? First step, make sure it isn't just basic sub, right? Basic substitution. I mean, look at your integral first. Don't get into the habit of where you're like, as soon as you see a polynomial over a polynomial, you're like, partial fractions. You know, always make sure it's not something clean first. Then, if degree of the numerator, I'm going to say num, is greater than or equal to degree of the denominator, do long division first. Once you've done long division, you can move on to step 3. Or if there is no long division, you just move step 3. And then there are going to be choose correct decomposition of expression. This is the most difficult part of it, all right? Is we have to figure out how we're going to try and decompose this thing. To give you an idea of what this step is, let me show you right here. You know when we were looking at this right here and we factored it and we said, each of these were distinct linear factors, so we did this? That's the part of the problem where I'm saying you have to choose the appropriate decomposition. This was choosing the appropriate decomposition. And then after you do that, you go figure out what everything is. All right? Understand? The book talks about 4 different cases that you could run into. 4 different cases. So I'm going to put that in my little list here. You could have case 1 where you have, I want to follow the book's language here, distinct linear factors. Distinct linear factors. So I think the best way to show you this is to just give you an example of what that is. So right under here, example, what if you had something where your denominator was like x plus 1, 2x minus 1, 3x plus 4. And then on top, it really just doesn't even matter what's on top, okay? I don't care what's on top. The bottom are distinct linear factors. Distinct means all different, right? And linear means they're all linear, right? Factors means they're multiplied, right? Each one of them is a factor. If you have that, the correct decomposition of that is going to be to create however many distinct linear factors you had, and then above each one, what? A letter, A, B, C. So if you had 4 distinct linear factors, A, B, C, D. If you had 10, right? A, B, C, D, E, F, G. If you had 40 distinct linear factors, A1, A2, A3, A4. And that's why we use notation like that in math, right? So we don't run out of letters. But just for the sake of us, you're never going to go past like F, okay? Today we won't ever go past F. Understand? That's case 1. Now, that you could have this along with more crap, okay? But for every distinct linear factor you see, you have to create that. Now, case 2 is where you have repeated linear factors. So that would be something like this. Again, I don't really care about what's on top. What if I had x plus 1 squared x minus 4 cubed? So I have linear factors, right? They're repeated. Repeated means that's x plus 1 times x plus 1, so it's repeated. That's x minus 4 3 times. So the way you do this is that you look at the number, right? Here I have two of those. If I just had one, what would I do? If I just had one of those, what would I do? I would do a over x plus 1. But because it's a repeated linear factor, I have to do another one over x plus 1, but this time squared. So I have to do an a over x plus 1 and then bring the power up, b over x plus 1 squared. And I stopped there because it was squared. What do you think I'm going to have to do for this one? Same thing. So what? C over x minus 4, now bring up the power, d over x minus 4 squared, and then, yes, you're not seeing things, e over x minus 4 to the third, and that's when I stop. Think about what you'd have to do to figure this out. Think about the common denominator and how ugly this is going to be over here. All right, so that's case 3. That's case 2. Case 3 is, what do you do if you have an irreducible quadratic factor? Irreducible quadratic factors. What does irreducible quadratic factors mean? Irreducible means you can't factor it. It's a quadratic that can't be factored. If it can be factored, then you'll have linear factors, won't you? But if it's not factorable, then it's irreducible, so you can't break it down. If that happens, then here's what we'll have to do. So again, I don't really care what's on top. Let's say on the bottom I have x squared plus 1, and then x squared minus x plus 5. Those are both irreducible quadratic factors, right? You cannot factor the sum of squares. And this one, you could check the determinant of this one would be negative. You remember determinant is in the quadratic formula, the b squared minus 4ac. That part, b squared minus 4ac, is the thing under the root. If you look at what b squared minus 4ac is here, it's negative, which means this doesn't factor. So that's irreducible. And that means that we can't break into linear factors. So what do? Well, here's what we do. You're going to love it. We put ax plus b over the first one, and then we put cx plus d over the next one. Essentially, what have I created? I've created a linear expression on top of it. Why? Why would I do that? Because what's the derivative of a quadratic? It's linear. And didn't we do something like that earlier? So if we do this, we should be able to squeeze an answer out somehow. We might have to really screw at this a lot to make it work, but we should be able to. And then case 4, last one. What do you think would happen if you have a repeated irreducible quadratic factor? You have to go one for each power, right, and keep the powers coming up. So this is case 4 in our final case. Repeated irreducible quadratic factors. And I'll just show you one. If we had that, then I would have ax plus b over that, right? The quadratic. Then what? Separate one, right? Cx plus d, good, over this time squared, plus, then lastly, maybe ex plus f over x squared minus x plus 5 cubed. And I stopped because I got to cubed, right? All right. That's it. That's all you have to do. If you know. We haven't even done the work yet. We haven't even really done one of these, right? So shall we? Our first example. I need a break, don't you? Y'all ready for spring break? Oh, wrong semester. Oh, here we go. Integral x cubed minus 4x minus 10 over x squared minus x minus 6 dx. What do y'all think of our test being a 2-day test? No? Like a whole week? You like the idea? We'll just do like a Monday or a Tuesday, Thursday test. Tuesday you do part of the test, Thursday you do the rest of it. Take home. All right. Well, we can divide. Do we need to? I sure as heck don't see anything easier to do, like simple substitution or anything like that, right? I don't see any of those forms for trig sub like square root x squared minus a squared. Throw all that out the window, right? Integration by parts? No. But we have a polynomial over polynomial. The degree up here is higher than this one, so long division to start. All right, start with long division. All right. X cubed plus 0x squared minus 4x minus 10. Out here is x squared minus x minus 6. What do I multiply x squared by to get x cubed? X, put that out here. Get x cubed minus x squared minus 6x all over. Now change the signs, minus, plus, plus. Add down, we should have x squared plus 2x, and then bring that minus 10 down. Now, turn x squared into x squared, I just need to multiply by 1. And that gives me exactly x squared minus x minus 6 all over. Now, or not all over, subtract, which changes the signs. And when I add down, I get 3x minus 4. Agree? Okay. That's my remainder. I stopped there because the power of the remainder is lower than the power of what I'm dividing by. So I put up here plus 3x minus 4 over x squared minus x minus 6. And that's my new integral, right? That's going to be my new integral. And I'm supposed to be happy about that. So I'm going to try and integrate now x plus 1 plus 3x minus 4 over x squared minus x minus 6 dx. Go with me or not? We good? Okay, 2 of those are going to be easy, right? These 2? So I'm going to start putting my answer, and I'll have to come back to it. 1/2 x squared plus x plus, and I'll leave a space there, and we'll come back with the answer. We're going to go do this integral on a different paper, on a different page. Here we go. I'm now working on this new integral, 3x minus 4 over x squared minus x minus 6 dx. So now I'm going to start going through, we were doing the partial fraction steps here. We did long division, right? When we did that, we got something we could work with, but what we have left now can't do long division on that. So now let's go through and start looking at our cases. What do we have in this particular case? We have to be able to factor out the bottom, right? The denominator factors, x minus 3x plus 2. Agree? And those are, what do we call those? Distinct linear factors, right? Distinct linear factors. So I say, hold on, partial fractions. I need to take 3x minus 4 over x minus 3 times x plus 2. I need to turn that into, I will have 2 pieces, one for each distinct linear factor. I will have 2 constants on top. Oh, what do you think? Yes? So doing a quick multiplication of both sides by the LCD, I have 3x minus 4 equals a times x plus 2 plus b times x minus 3. This problem is not very complicated when it comes to trying to put these together, so that's why I'm going quickly through it. When it gets a little more difficult, maybe not today, but next week, then we will, I'll take a little more time through it. How would you like to figure out what a and b are here? Yeah, let x be something, and let's do that. So if I let x be, let me kill off b first, okay? I don't know why I like to get a first. You could get b first if you wanted to. Let x be 3. And we get what? 5 equals a times 6, and then plus b times 0. So what's a? 5/6. A should have been what? Oh, it should have been 5. It would have been more fun if it was a fraction. It would have been okay. All we would have done is pulled that fraction out when we did the integral. We just would have pulled it out of the integral. So A is 1. All right, now let me let x be -2 so I can kill off the A. What do we have? -10 equals -5b. So b is 2. So back to that integral. That integral now becomes 2 separate pieces. It's a, which is 1, over. Now make sure you get this correct. A was on top of which factor? The x minus 3. So on top of the x minus 3, and then plus the b, which was on top of the other factor, which was x plus 2, dx. And do you feel good about integrating those? Okay. Natural log x minus 3 plus 2 natural log x plus 2, and plus a constant, but I still need to go back and tack this on to the other problem, right? To the other part of the answer. But we're there, right? We're pretty much there. It's fun. Kidding. It's tedious, right? Yes, I will. I just threw it on to the other part real quick. There's where we were. I'd like to show you one example of the repeated linear factor, and then what we'll do is, if there's time, we'll do a little in-class assignment. You know, if not, we might not have enough time. We'll just see how long this takes. I'll show you, basically what I want to do is show you 2 of the cases today, and then when we come back, I'll show you the other 2 cases, and then our test is what, a week from Monday, or is that right? A week from Tuesday? When's our test? Yeah, so a week from this upcoming Tuesday is our test. So we'll be able to finish everything up on Tuesday. We'll be able to spend Thursday talking about the test next week, and then we'll take the test. And that's going to be, you'll know where you are after that test, right? I mean, that's usually a really, really big test for Cal 2. It's that first one. All right, repeated linear factors. I've got a lot of old stuff. I could kind of try and fish something up. The problem that I have with practice tests is that it narrows people's focus too much. But then at the same time, if I don't narrow it for you, sometimes people have trouble figuring out what the heck to study, you know? This test that you're going to take in a week and a half is one of the more challenging tests to create because there's just so much to pull from. So if I make a test of, 6 to 8 integrals that I think are good, you may look at them and be like, man, I didn't even study that, because there's just so much here that, right? I could do 2 integration by parts and you spent more time on other stuff. And so it can become dangerous in that sense. That's why the idea is that you really understand each concept well. That's the point of the test. All right, so what are we going to do? We look at that, not thinking U substitution here. I'm not thinking trig, right? I mean, it's pretty clear now, hopefully. Now, do I need to do long division? What's the degree of the denominator? It's cubic, right? That's linear. This is actually quadratic. We put them together. It's cubic. So I know that together all of this is third degree, and up here it's second degree, so I can't do long division. So I'm ready to go straight to my partial fraction, right? Partial fractions. So I'm going to write this down. X squared minus 5x plus 16. You know, one thing I didn't do that I should have. I should have checked to make sure the top didn't factor. Because what if it factored and one of these canceled? Like, you know what I'm saying? That's not going to happen. But, you know, I should have thought that first. All right, so up here we have what? A distinct linear factor, right? And then we have another one that's repeated. So remember I was saying you could have like case 1 and 2 together? I have case 1 and 2 exactly together. I have distinct linear factors, but one of them is repeated. So what I'll have to do is for that first linear factor, 2x plus 1, I put a letter on top of that. Then I have to do b over the other linear factor, and then a c over the other linear factor, what? Squared. What is the LCD, the least common denominator? What are you going to multiply everything by, both sides? It's that 2x plus 1x minus 2 squared, right? Just remember, this is what you're going to multiply everything by. So it cancels everything on the left, which leaves you with x squared minus 5x plus 16. On the right, though, just be careful here. When you multiply this LCD times this, only the 2x plus 1 cancels, which leaves you with what? Ax minus 2, but squared. Plus, now what about on the b? 2x plus 1, and then you still have an x minus 2 there, right? Only one of them went away. Only one of the x minus 2's went away. And then here, 2x plus 1. It was plus, right? Yeah. Questions on that? Now, here's where I said you could run into trouble with that one method. What if I'm trying to get A? If I'm trying to figure out what A is, that means I have to kill off B and C. What's the only way I can kill off C? If I let X be what? So what would that be? Negative 1/2? Negative 1/2? So set that to 0, you get X is negative 1/2. So if I let X be negative 1/2, it'll kill this off, right? And it kills this off, right? Which is good, yes? However, if I had tried to get A by killing off B and I said, hey, let X be 2, right? Then it would have also killed A. So you have to be careful what you pick. Let me see. This one is actually going to work out. There's a way to kill off everything. Oh, no, hold on. Can you get B? You can't get B by itself. Why? To kill off A, you have to do this, 2. And to kill off C, you have to do this, negative 1/2, which means you wind up killing off B also. Y'all follow that? But it's okay because we're going to be able to get A, we're going to be able to get C, I believe. So let's just try it. Let's see where we go. But I'll be honest with you. For me, this plugging in stuff is real nice. If it works right away, I like it. But if not, I just make a system of equations and get my calculator out. That's what I do. But we're gonna try this. Let's let X be negative 1/2. Got to look at another issue we're going to run into is what? We're going to have to do negative 1/2 here, negative 1/2 here, right? Negative 1/2 here. I want to go to my roots here where I feel comfortable. I mean, we could do it. It just seems like more work. So I'm going to show you. I think I want to do it the other way. Is that all right? If you want to, you know, go and do this on your own, you know, trying to let x be something, there's nothing wrong with that at all. So first thing I'm doing is I'm cleaning up everything on the right side, distributing. Let's see, I get 2x squared. I get minus 4 plus 1, so minus 3x minus 2 plus c times 2x plus 1. So before I actually did anything, I actually squared this, and then I foiled this, and then I didn't touch this. And then I'm going to distribute my a through, my b through, and my c through. When I distribute a through, get ax squared minus 4ax plus 4a plus 2bx squared minus 3bx minus 2b plus 2cx plus c. Do you agree with that? Now that all has to equal the left side, which is just x squared minus 5x plus 16. What am I supposed to do now? What did I do previously? Put all my terms together. So I want to put this ax squared together with this 2bx squared. Do I have a cx squared? No. So if I put those two together, right, and factored an x squared out, what would I get? A plus 2b, and then I'd have that x squared that I pulled out. That's what these two together, side by side, pulling the x squared would look like. How about my x terms? Negative 4ax, negative 3bx, and plus 2cx. So if I write that down and pull the x out, in parentheses I would have negative 4a minus 3b plus 2cx. Do you agree with that? Do you have any questions on what I did? And then the only thing left are all the things with a's, b's, and c's, but no x's. So I can just put those all in parentheses in its own group of, its own set of parentheses. 4a minus 2b plus c. That has to match the left side. And so now I'm going to match coefficients. That's really what I'm doing here. The number in front of x squared is what? It's 1, so I need this right here to be a 1. The number in front of x is negative 5. I need that to match up with this. And the number by itself is 16, which needs to match with this. Yeah? How many equations am I going to have? How many unknowns? 3. Let me write down my equations, and I'll write it as a system of equations. I'll make sure I'm in alphabetical order here. The first equation says a plus 2b must equal 1. Next equation says negative 4a minus 3b plus 2c must be negative 5. And then last, 4a minus 2b plus c must be 16. Now, if I could just solve that system of equations, I'd be done. All right? There's a calculator that I can borrow real quick. I'll just do it on yours. I'm going to solve it, and then I'll tell you how to do it, okay? Almost done. The solution is A is 3, B is -1, and C is 2. Okay? Now, would you like to know how to do it on your calculator? All right. Here's how it's done. Now, is anyone not using a TI? Everyone's, what do you got? Casio? No? Is that, it's a TI? Inspire, okay. That one, I think you just talk to it. Solve system, you don't do that. But can everyone at least see your screen? It's going to be a little different for everyone as far as how to do this. And look, I know some of you already know how to put matrices into the calculator and all that stuff. The method I'm going to give you should work on everyone's calculator. That's why I'm giving you this method. What you have to do is you have to go into either your math or a matrix menu. And that'll depend on your calculator. It's a menu that says matrix or something on it. You see your matrix menu there? If you get your matrix menu, then raise your hand. I'll come by and... Okay, yeah, all right there. Just wait, are you there? No, it's the matrix, so you have to hit the orange button and then that one. You're there. Did you find it? No? I need to turn the lights on in here. Hold on. How much time do we have? Yeah, you were there. You're there. The heck is that?
That doesn't sound right.
No, matrix is the orange one, so you have to hit the orange button and then that little X -1. Who's not there? Who's not there? You're there. Okay. So you should be at some. A lot of you are at a screen where on the top there's now an option for math. Yours does not, unless you're ready. So you have to move to the right to get to it. Yes, move to the right to get to math. You're ready there. Move to the right to get to that math. Good. What happened there?
So this is the matrix, and then this is another screen.
Let me see that. Oh yeah. Yeah, you're there. Did you get there? Okay, math. And then now you want to try and find a command that on most of your calculators looks like this. RREF. It's reduced. It stands for reduced row echelon form. And yours actually says it there, right? Okay. So once you select it, go down and actually hit it. Now there's one above it that says REF. Don't do that one. It's RREF. So scroll down to it, hit enter, and you should now be sitting at a screen back on a home screen where it says, I'll do it in a different color because now we're at our home screen, RREF, and it should have a parenthesis. Are we all there? Okay. Now let me explain what's going to happen. We just told our calculator that we would like for it to basically do something to a matrix called reduced row echelon form, where it gives us the solutions, right? But we need to give it the matrix. So the way we do it is you now will enter a bracket. Now the bracket, I believe, is on the right-hand side near the multiplication division keys. Multiplication, subtraction, above the multiplication and subtraction, there's the bracket. You all see it? So you have to hit the little like shift button first. Okay, that bracket, the first bracket, what it says is, here comes the matrix. All right, here it comes. Then you do another bracket that now tells it, here comes the first row. And now what you do is you start typing in the numbers of the first row of this system of equations. So what are the numbers in our first row? The numbers are the things out in front of the letters A, B, and C. So what are our numbers that are in front of A, B, and C in our first row? 1, 2, 0, 1. And you put commas between them. So it'll look like this. 1, comma, 2, comma, 0, comma, 1. You see how important it is, though, to have that 0 there? That 0 is the coefficient of the C. Now, I think it's above the 7. Is that right? Oh, yeah. You don't even have to hit shift for yours. All right. What do you think comes next? Close the bracket to tell the calculator I'm done with the first row. And then open bracket to say here comes the second row. And then type in the numbers on the second row with commas between them. So what would the numbers be? -4. So make sure you use your negative key, not your minus key right now. Know the difference between the negative and the minus? So -4, -3, 2, -5. -4, -3, 2, -5. Then what? Close the bracket. Now, open bracket. I'm going to have to continue on another line here. Open bracket, what? Last row. 4, comma, -2, comma, 1, comma, 16. 4, comma, I already forgot. -2, 1, 1, 16. Close bracket, that ends the third row. Close bracket again, I'm done with the matrix. Close parenthesis, I'm done with the function. I know that seems like a lot, but you see how fast I did it? Okay, once you understand and get used to it, it goes pretty quick. And now just hit enter. And it depends on your screen. Yours is, yeah, the actual matrix. You have a matrix there. You see yours, matrix, matrix. Everyone's got a matrix. No one has a row of brackets and stuff, do they? Okay, so look at what this thing says. What you should see here is like 1, 0, 0, 0, 1, 0, 0, 0, 1, and then you should have the 3 answers. What are they? Okay, so does it make sense? Look, this is still a matrix. This is still the A, the B, the C, and then the equals, and then the number. If you have 1 in front of A, that's A, right? And then 0, C, 0B, 0C, so that's just A equals 3. This one is saying what? B equals -1, and this one is saying C is equal to 2. Now, for those of you who are going to take more math, we're going to take linear algebra. This is what we call the reduced row echelon form. What you're trying to do is take a matrix and turn it into what we call the identity matrix, which is ones down the diagonal, zeros elsewhere. Because when you do that, you basically have solved a system of equations. So you do a bunch of operations to make it look like that. All right. So back to the problem. So our integral, way back up here, I'm going to rewrite that integral on a new page. I'm going to copy and paste it, which is kind of cheating. This becomes integral, A was 1, 3, whoa, way off. It was that over 2x plus 1. And then we had plus B, which was -1 over, it was the first the first repeated factor, and then plus 2 over the repeated linear factor, but this time this squared. Did I place that correctly? Is that everything? Yes. Yes, you could put the negative right here. Yes, absolutely. I just wanted to put exactly, A, B, C the way it appeared. And now, hey, we're in business, right? 3 halves natural log 2x plus 1. What happened? What happened? What happened? 3 came out, right? This is ax plus b, so we had to come through with that 1 over a to compensate for that 2 out here. So 3 halves, and then just natural log of the linear. What about the next one? Minus natural log x minus 2. That one's just pretty straightforward. And then the last one, be careful here. Negative 2 over x minus 2. Look back at the very beginning of class. I did a problem very similar to this. We're done. How do you check your answers, see if it's correct? Well, you would have to take derivative, which would give you this, and then you would have to get a common denominator, and it would give you this. So do you all remember learning partial fractions back then? I mean, this is why you actually learned partial fractions back then, is because of Cal 2 later. You need it. All right, we are out of time. So I don't know where the time goes, you know. For homework, page 334, I'm going to try and just give you problems that you can do now. 7 through 11, 15, 17, 19. All of those you should be able to do because they're all distinct linear factors or at the most repeated linear factors, but none of them are quadratic yet, and that's what we'll talk about next time. All right, have a good one.